Thank you very much. As mentioned, my name is Daniel Trier. I come from the Danish consulting company, PlanEnergy. And we're specialized in planning of intelligent energy systems, integrating different components and sectors to optimize efficiency and increasing the share of renewables. So in terms of the agenda for today, let me see if I can modify this or change the slides. Otherwise, I'll have to see if, yeah, now I think I have controls. So, let's say, sorry, 1 second. Am I able to flip to the next slide? There we go. So the scope of the analysis that I will talk about is the network layout within different urban environments, and this subtasks. This task is sort of split into two subtasks, where one being investigating which type of urban environments are we talking about, and the second part is the design of the network itself. So moving to the first part of this analysis regarding the different towns and, let's say, settlement typologies, meaning the different part of the towns, which can be very different from the average of an entire town. So in order to test the FLEXYNETS concept in different contexts, we've analyzed different towns and not only the towns as a whole, but actually also split in different sections of the towns. And this is used to understand how FLEXYNETS can be feasible, applicable for different urban environments and in different locations. And this first part of the analysis has been carried out by extracting data from different databases and by means of GIS-based software, which I will explain about in a minute. As mentioned, we're not only looking at average values for an entire town, but since one of the ideas behind FLEXYNETS is that it should be easily scalable, we are also looking at a small part of the town, and then we can always expand from that. So the methodology has been, as I'll explain now, first of all, we split the town examples in 4 different categories. And as you can see here, in small towns, medium towns, large towns, and then bigger cities with more than 1 million inhabitants. And the approach is sort of semi-automatic, which means that we have combined different databases. One of the databases is municipality planning, which defines the typical use of a certain area, and a second, let's say, second layer added on top of that is a so-called heat atlas, which defines the demand on an annual basis for each building and the location of that. So combining these, by combining these, we can know exactly how the demands are distributed over the towns and in the different typologies, sectors of the towns. I will show an example in a minute. So these type of typologies that I'm talking about is, as shown here, split in 4 different main categories, and within these even subcategories are included. So we're not only talking about, this is a residential area, but we're also looking into, is it a suburb or where the households are distributed a lot, or is it a downtown high dense area with high-rise buildings and so on. So this way we have these topologies we have applied to all the different part of the towns, and one example here is Sønderborg, a Danish town of approximately 27,000 inhabitants, covering an area of approximately 13 square kilometers. The red area is just what is defined as a town area, and applying the typologies I explained about before gives us this result, where we can see that the center of the town is the dark blue one on the lower left part of the town area, whereas the yellow ones are the industry areas where we could expect to see some sort of excess heat facilities or availability. So, and on top of that, we apply the heat atlas defining the heat demands for every building in this town. And the outcomes of this is that we have analyzed a total of 15 different towns and cities, and then each disaggregated by means of the 10 different settlement typologies, and then defining the heating and cooling demands and the share of each typology in the different town sizes. And this gives us then either entire towns to investigate further to analyze the FLEXYNETS concept for, or part of the towns. As mentioned, we could choose specific typologies to investigate. And as we have gone through this list of different towns, we see similarities within the country specifically, but actually there are great variations between different countries. And it seems like this is not only weather conditions that affects the differences in demand, but also that insulation levels are typically higher in Northern European countries, which somewhat compensates for the colder climates. And the amount of older non- or low-level insulated buildings is also very different from country to country, and even from town to town perhaps. And also, what does high-rise buildings mean? In some countries, a high-rise building would be 3 or 4 stories, whereas others would define that as 7, 8, or even more. So the high-density areas might even be very different from country to country. So this just tells us that when designing the district heating and cooling networks in practice, it's very important to take the local conditions into account. Moving on to the next part of my agenda in terms of the network design. This is the structure of the network design approach, where we combine conventional district heating with the FLEXYNETS concept, because we feel that even though we might identify suitable configurations to make the FLEXYNETS concept feasible, we would like to avoid the question arising that why don't you just go for a conventional district heating in this area? It might be even more feasible. So in order to be ready for that kind of answers, or let's say in other words, defining where is FLEXYNETS more feasible compared to district heating or conventional district heating or individual heating. So in order to be ready to answer that, we have compared also with conventional district heating network layouts. And not only this comparison has been made, but also different structures of the network itself, where we compared traditional tree structure, where we have this branches going out from the center part where the supply point is, typically the district heating plant. Compare that as one option with a ring structure where we have a geographical ring throughout the town area, and several smaller branches or twigs sort of growing from that ring. And I will show examples of that in a minute. Here's one case or one overall map of the analysis for Aarhus, which is a town in Denmark with approximately 260,000 inhabitants. And what we did here was taking two examples from this town, one example in the outskirts and one example in the city center. So the first case in the Aarhus one is the lower left one in the southwestern part, where we applied a ring structure to make it possible to reach every consumer in this area. And it might be a bit hard to see, but this is just an example of let's say the tree structure, where we have centralized supply points and branches to reach all the consumers from that. And similarly, when applying the ring structure, we also need to have branches going from the ring out to reach every consumer. So this kind of comparison between the different structures and as well the different temperature levels in the FLEXYNETS versus the traditional district heating temperature levels. And the second case of course is city center. And here we have the purple area is due to the fact that we have the red area as a background defining the town, and then on top of that the dark blue one, which means this is a city center, a high-rise, high-density demand area. So the purple area is sort of the city center, and we applied then the ring structure in different geographical diameters, where we have here a larger one and a smaller one to see also how big should such a ring be. Another case is another smaller town where we have approximately 71,000 megawatt hours in demand in the district heating network that is existing already. And here we then apply also a ring structure to check this. So this is just for you to get a feeling of how we apply this analysis at this point. So checking the feasibility, we compared the different options, and it's very clearly seen that investment costs will affect the feasibility, meaning the network, how much does the piping cost, and the prosumer heat pumps needed to rise the temperature at the consumer side, and so on, and also operation costs, meaning what does the electricity cost to supply the heat pumps at the consumers or prosumers, and also the electricity for the network pumps to circulate the flow in the FLEXYNETS network and also the district heating network. And it's also a matter of market pricing approach, which type of financing options is available, which type of ownership would be possible, which is also something that we investigate in the FLEXYNETS project. So as mentioned, local conditions will have a significant influence on the feasibility, as well as what would be the optimal solution in a given situation. Is there a large cooling demand, meaning is there usable heat sources available from the cooling processes, and these heat sources or other excess heat facilities, how are they located? Are they spread a lot across the town area, which would lead to an increased feasibility for the ring structure, because then a larger number of supply points could be reached by the ring, so it becomes easier to feed in with excess heat to this network. But if you only have one centralized excess heat facility you need to reach, then the ring structure might be less feasible. And what temperature levels are we talking about, and are the settlement typologies uniform or scattered, and so on. So we see a lot of different local conditions affecting what would be the optimum solution. Also, as you saw before, the different, let's say, geographical diameters of the ring structure. Is it a big ring covering a large part of the area that we investigate, or is it only located in the very central part of this area that we would like to cover with the FLEXYNETS concept? Well, that also affects the feasibility, and in general it seems like it's not feasible to place the ring at the very outskirts of this this area that we would like to supply, but you should rather place it more centralized in order to, let's say, supply both inwards and outwards with such a ring structure. And also more excess heat available for the FLEXYNETS system makes it easier to compete with traditional district heating. In other words, the feasibility of FLEXYNETS over the traditional district heating might be caused by the fact that you have a lot more excess heat available at the low temperatures that the FLEXYNETS concept needs compared to the higher temperatures required for excess heat to be applicable or available for traditional district heating. And also a ring structure seems to require a certain amount of excess heat to be reached by the ring, or a more high density area to make it feasible compared to a branch structure. And also, the detailed optimization of the different case will improve the feasibility, whereas so far we have more looked into the initial investigation and comparing different options, and the further work will also be about, let's say, more optimizing the concept. And regarding these next steps, this is a structure mentioned before. Yeah.
Can I ask you to conclude?
Yeah, I am very missing one slide more than this. So I will just mention that this is not only for this task described here, but we could also add on top of that some further financial costs to optimize for the lowest possible price for heat and cooling at the end. So the next steps will be different storage options also to influence that and optimize that part and combine with this analysis. And also more detailed network simulations will be carried out and different geographical locations will be investigated. So I will conclude on this and give the word back to the organizers at your. Thank you very much.
Thank you, Daniel, for taking the timing. Are there any questions to Daniel? I didn't see any on the screen. If not, and again, while we are waiting for questions on this topic, there was a concern on the previous presentation regarding the combination of gas boilers and heat pumps, which could hinder somehow or could reduce incentives applied to retrofitting buildings. I will reply to this briefly. When I spoke about a combination of heat pumps and gas boiler in final customers' buildings, I didn't mean that we are designing these combinations for new build or for retrofitted. Retrofitted buildings or new buildings do not need any gas boilers, as the temperature levels for space heating are sufficiently low as to be served by or driven by heat pumps. The point is that in a real built environment, not all the buildings are retrofitted or new, and based on the actual retrofit rates that we have over Europe, it is not reasonable to believe that our cities are going to be completely retrofitted in the next few years, tens of years, I would say. Therefore, again, what we thought is that we have to also have in mind combinations of existing gas boilers installed already in old buildings and new installed substations, including heat pumps and storage tanks. and one storage tank. In a way that again the gas boiler, the existing gas boiler, is able to cover the peak loads, the space heating loads, which cannot be covered by the heat pump itself. Therefore, the installation or the connection of all buildings would be made again with the same kind of heat pump substation, which takes also the control of the existing gas boiler to cover peaks, if this replies to you. And then in this case, the incentives shouldn't be, say, affected. Hopefully I replied to your question. Going on with the presentation, we have the first, oops, there's another question. Hi, Daniel. How do you assume the heat demand of the topologies if there aren't any measured energy consumptions available? Are we simulating or not? Daniel, I don't know if you want to reply to this.
Yeah, I can. I think I can do it fairly briefly. This heat atlas is based on a national database with the building register, defining which type of building are we talking about for every building in the country, actually. And the owner is obliged to update this if he changes his supply type. So we have the type of supply and also the average annual heat demand for that. So of course there are some uncertainties because it's not measured demand, but previous investigations on this uncertainty has shown that once you don't go too much into each building on its own, but have an average value for a town area, then it's actually fairly accurate to do it like this.
Yeah, and this atlas is quite typical or quite peculiar of the Denmark scenario, but these atlas are also starting to born here and there in Europe, over Europe, in Germany and other countries. So again, it is not that easy as Daniel showed to get this kind of data over Europe, but it is going to be in the next years. Exactly, very good data conditions in Denmark. Exactly.
Yeah, so let's say the majority of towns investigated are the Danish ones based on these availability of data, but we also include several from other countries to also investigate the differences there.
Okay, thank you, Daniel. Let's try to go